All right, with this module, we are going to look at what we term complex ceramic structures. That is, those that have multiple cations or multiple anions or both. And so this particular module, we'll look at the perovskite structure. All right, so we've seen table 3.3 a number of times, and I want to sort of draw our attention to the complex structures part of it, because these are the ones that we're going to talk about in the next couple modules. And so there's not a definitive list of complex structures, but these are just some common ones or important ones for particular applications. And so you can see perovskite, which we're going to talk about, and it gives it in the same kind of filling and same kind of scheme as we saw with binary structures. We have the anion packing, and you see that most of them, or all of them, are built on the same foundation. So cubic close packed. Then you see the coordination numbers here, and here, because there are multiple cations, you see multiple coordination numbers, not just 2 but 3 in all of these cases. And then same thing, you see the site occupied by the cations, octahedral, tetrahedral, some combination, and then you see some examples of those. So similar schematic, but again, we have multiple cations. And so we're going to look at the perovskite structure. And what I want to do is perovskite is named for calcium titanate, and you can see the formula up here. And so this is a sketch of the perovskite structure. So what I want you to do as an introduction to this section on your quiz is label the ions. So I'm not telling you which one is which. I'm telling you the formula up here, and then you try to match each of the ions to each of the positions. So do that, come back, and we will discuss. All right, so let's look at the results of this. So in general, perovskite has the general form AbX3. For the most part, they're oxides, so X is oxygen, so AbO3 you'll sometimes see. And then one of the prototypical structures is the calcium titanate, or CaTiO3. And so based on these, based on this stoichiometry, we can start to glean some things, right? There's 1 calcium, 1 titanium per 3 oxygens. And so, if each of these, the black one here, the white one, and the grayish one, if each one of those corresponds to one of the ions up here, you can imagine that the oxygen one is the one that's going to be most prevalent in the unit cell. And so that would be the white, because each one of these is counted as half. So 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, and that would get us to 6 1/2, so that's 3, right? So that's oxygen. So oxygen's pretty easy to count. The other, calcium and titanium, you see that the black one is inside the unit cell, so that is 1. And then if they're on the corners of a cube, they count as 1/8, so there's 1 atom there. And so the main thing you have to do with that is determine the relative size. So you can kind of see that these are larger, whereas this one's smaller. You can also work out the charge balance of this. So if we know oxygen is 2 minus, then you have to have a combination of +6. And so for these two, one of calcium tends to be 2 plus, and so titanium, that leaves 4 plus. And so if we look at 4 plus, 4 plus are generally smaller than 2 plus, and that's what we see. So this is just snippets from the table, the ion size table that's in your textbook. And so you can see that titanium has a very small radius compared to calcium, which is much larger, and it's similar in size to oxygen. So oxygen and titanium are similar in this regard. And so that's what we see in this arrangement, is that the cubic close packed is actually calcium plus the anion. And that's what forms the FCC arrangement. The anions plus the A site, which is the larger of the two, the calcium. So some examples, there's a lot, like I said, a lot of oxides, calcium tin, sodium tungsten, yttrium aluminum. There's a number of perovskite structures. So let's look at the coordination then. So the starting with the A site, we know the A site, this is ABX3. So A site is calcium. And again, the calcium were the gray. And so if we look at those, then our coordinate, this is in the cubic coordination, right? It's on the corners of the cube. And it's going to be coordinated by the oxygens. And you can see 3 of them here. But if we draw more unit cells, we'll see that there is a total of 4 below it, 4 in plane, and then 4 above in these situations, the FCC arrangement, basically, right? So we think about the coordination number of FCC, and we get 12. So I would also recommend drawing that out if the 12 number is not working with you. So I might recommend drawing that out and hopefully prove to yourself that coordination is 12. For the B side, it's a little easier because we're talking about the titanium in the center, and you can see it's surrounding by the you can actually see they show the octahedron there, so you know it's 6 in that case. But again, you can also, the smaller an ion, the less it's going to be surrounded by. So it makes sense that the small ion is coordinated by 6, and the larger one is coordinated by 12. All right, so again, the structures that have this, like calcium titanate, and so you can see the octahedron shape for the B atom in this case. And one thing I kind of wanted to mention about this is that this octahedron, if there's a relatively large cation in that site, so titanium's quite small, but if it's relatively large cation occupies that site, we actually get some tilt to this shape. And what that does is it actually results in some interesting electronic properties, result in piezoelectricity. So, excuse me, if you're familiar with certain sensors and so forth that measure strain, a lot of these, that measure force, it does it by this piezoelectric property, in which an applied force results in electronic properties which we can use in sensors. And so if you're thinking of those types of materials, the perovskite is what gives it that interesting property, and it's because of the sort of tilt in this octahedron that we have that gives us these unique properties. So perovskite structure is very important for electronic ceramics, and you'll often see this come up when you deal in those types of electronic ceramic applications. The other interesting thing about the perovskite structure is that right with the perovskite structure, we had an ABX3 or ABO3. However, if we have even more different cations, we can actually make this even larger structure. And so I wanted to kind of show you this, because if we think about this yttrium, barium, copper oxide, or what we often refer to as YbCO. This is a superconductor, meaning that it has zero resistivity at below its critical temperature. This is based on a perovskite structure, like it's kind of highlighted here, but we have multiple different we have even more cations. You can see we have 3 up here, and so they alternate in the different perovskites. So you can see one different one here and then another here, and so you have an even bigger unit cell. So it's not cubic anymore because it basically contains 3 different sub cells, which forms the unit cell. But that gives this perovskite is the basis for that much larger complex structure that you have for this YbCO superconductor. And it gets, when we talk about superconductivity in these oxides, in these very complex oxides, the structure gives it the ability to conduct these electrons in the way that it does. So I'm not going to go into the detail here, but you can see the different sorts of coordinations of copper and oxygen that you have in this structure. Those act in such a way that gives it the properties that result in conductivity. And so the structure is related to that in these cases. And the main difference is that central cation, either barium or yttrium, is alternating in the other parts of the structure.